Assalamualaikum warahmatullahi wabarakatuh. Praise and gratitude to Almighty God who has given us health and opportunity with despite the coronavirus outbreak. We can still attend the seminar activity in online. Thank you for the opportunity given to me. Nay, Jacob Patrick Batil from STT Mandala, Bandung. We represent the author team to present our journal paper, and title is Electrical Energy Alternative of Magnetic Field Around Wire of Power Line. The breakdown first. Electrical energy crisis and consumer needs. Consumers are increasing, while the availability of electricity is decreasing. Second, the existence of electric line with alternating electrical current generates and large magnetic field around and along the power line that store electrical energy, but that has not been utilized. The third, there are public concerns about the danger of electromagnetic field radiation near the location of the power line. And then, purpose of this journal is first, utilizing the magnetic field that is on the primary power line and making it a new source of electrical energy. Second, making an equipment that can take the magnetic field flux into the alternative magnetic power-based field with a voltage of 220 volts to provide electricity to the community near the location. The third, changing people image about the danger of electromagnetic field radiation. And next, the basic theory, understanding in electromagnetic field technology on electric power line in based on Maxwell law, Faraday law, and several other laws. The basic theory, understanding in electromagnetic field technology on electric power line is based on Maxwell law, Faraday law, and several other laws. Next, illustration of electric energy around the power line. Figure 1 shows the conductor rod that is electrified. Then around the conductor, it will be generated by a magnetic field around the conductor, circular pattern, and the direction of motion of the magnetic flux is to follow the rule of the right hand Fleming. By Maxwell law, we can see the figure 1 is the conductor in the hollow in then by Maxwell law, if electric current flow in line will generate a magnetic field at along the wire with a magnetic field encircling the wire, like figure 1 is one conductor with a current, electric current flowing in the to generate a magnetic field around the wire and the circle the forces. We'll look at figure 1. By Maxwell law, if electric current flow in wire will generate a magnetic field and at along the wire with a magnetic field encircling the wire. By Maxwell law, we can see in figure 1 of the conductor with current flowing into. And then by Maxwell law, and then by Maxwell law, Maxwell law says that the circumferential integral of intensity of the magnetic field is equal to the area integral of density of the electrical current flowing in the wire with the cross sectional area A. In the picture, it is shown that the circle of magnetic field will depend on the strength of the current flowing in the wire. Intensity of the magnetic field lost is on the outer circle of the electrical wire. And then, by Maxwell law, we can see the figure 1. Maxwell law says that the circumferential integral of intensity of the magnetic field is equal to the area integral of electrical current density that flowing in the wire with a cross-sectional area A. In the picture, it is shown that the circle of the magnetic field will depend on the strength of the current flowing in the wire and the intensity of the magnetic field. The lowest is on the outer circle of the electrical wire. And next, the magnetic field intensity is the equation 3. The H is intensity of magnetic field is dependent of the current flow in the power line I1 and winding of the power line and radius of circling the magnetic field around the wire. And next, how to take away the magnetic field energy? We use toroid. Toroid is equipment that functions the same as a transformer. However, with the primary and secondary coalescence in a number of turns of the copper wire. This coil is used as a secondary winding or N2, which are connected to the load lamp, and the electrical power line wire is passed into the toroid cavity as a primary coil or N1 with low primary current I1. As in the following picture is a toroid with the incandescent lamp as a load. The physical size of this toroid will determine how much magnetic energy can be taken. The greater the diameter and thickness of the toroid, the more magnetic energy will be taken. And then, if we want to determine how much power the load or light can be supplied with a voltage V2 equal to the rated volt of the 220 volts light, then the equation is equation 12. Then electromagnetic power the enters toroid is the products of V2 asterisk E1 and N1 divided by N2 V2 and K. K is a constant related to the nature of the toroid material. P2 asterisk is rating power of incandescent lamp or level of lamp in watt. V2 asterisk is voltage in rating of incandescent lamp or level of lamp 220 volts. Next, and furthermore, this is the voltage they occur when a magnetic field supplies a load, which in this case is an incandescent or electronic lamp, see in equation 18. In equation 18, it means that to supply the load with power P2 asterisk at a voltage of 220 volts required primary current that is equal to I1. In another sense, that the current of the power line will be able to generate power at the load by P2 asterisk at a voltage of 220 volts, or the value of the voltage that can occur in the load mounted P2 asterisk watt in the secondary side of the transformer toroid. And next, simulation experiment in laboratory. In the experiment, we did two ways to get the data needed as follows. Experiment 1. Simulation experiment in laboratory. In the experiment, we did two ways to get the data needed as follows. First, experiment 1, the system used in an induction motor as a primary line wire load to obtain large current flowing in the primary line power line, because small electrical current cannot produce enough magnetic field energy to light the lamp normally. In figure 3a. And experiment 2, using an alternating current voltage regulator and a step-down transformer whose secondary side is short-circuited through an electrical current meter to obtain a large and varied current on the toroidal primary side and to find out how much current must flow on the power line so that energy magnetic field can produce a normal voltage of 220 volts at the load on the toroid secondary side in figure 3b. And next, experiment result. From experiment 1, the experimental result that the primary burden in the form of three-phase motor in normal running state shown in table 1A. In table, we can see incandescent lamp 5 watt. The fault occurred in lamp is 160 volt. Description dim. Incandescent lamp of 10 watt. Voltage occurred in the lamp is 60 volt. Description dim. And the electronic lamp 7 watt. The voltage occurred in the lamp is 200 volts. Description lamp is bright. And all the lamp to receive to take a current in the power line is 27 amperes. And next, experiment 1B. The experimental result in table 1B that current I1 is value of starting current of three-phase motors use a toroid type 1. Experiments 1B is intended to find out how is a greater current flow through the power line, what is the state of the lamp, whether it is bright or dim, but with a current of 80 amperes, the incandescent lamp 10 watt, the voltage is 230 volts, and the condition is very bright. And the lamp, incandescent lamp of 40 watt, have a voltage of 225 volts. The state of the lamp is also bright. But for electronic lamp of 15 watts, this was not detected because suddenly the lights went out. It's just guessed that the current voltage is greater than 250 volt. The lamp is explode. And next, experiment 2. In experiment 2, we using an alternating voltage regulator and a step-down transformer whose secondary side is short-circuited through an electrical current meter to obtain a large and varied current on the toroid primary side and to find out how much current must flow on the power line so that energy magnetic field can produce a normal voltage of 220 volts at the load on the toroid secondary side in figure 3b. In table 2, we can see that for the incandescent lamp of 40 watts, 2 product voltage to those 220 volts, the needed current is 70 amperes. Incandescent lamp 60 watts, and needed current is 105 amperes. An incandescent lamp of 100 needed current is 175 amperes. But electronic lamp is 7 watt and need current is 30 amperes. And the older lamp light and voltage 220 volts. The value of the current in table 2 above is the large excitation current is required to flow on wire of electricity to power the light button toroid size or type 1 at the price of normal voltage of 220 volts. It can be analyzed through the characterized curve. Current wires primary I1 and toroid load voltage VL for some great nominal wattage of incandescent bulb or lamp following characteristics like graphic of experiment in figure 5. We can see that from the table 2, a graph is made of the relationship between primary current I1 and voltage on V2 lamps which are T size or incandescent lamp. For the 100 lamp, a graphic in red color and 60 watt in the blue color and 40 watt and black color. From the analysis, the conclusion, the magnetic field energy along the power line can be utilized as alternative electrical energy using toroid. From the analysis through the a linear approach that in power line with large current up to 100 of amperes can be obtained power up to several kilowatt at 220 volts. The greater the electric current that flows in the power line, the greater the magnetic field energy around the power line. And second, the more toroid is installed along the power line, the more new electrical energy will obtain. Three, utilizing magnetic field energy in the power line will reduce the public's image of the danger of electromagnetic field radiation near the power line transmission line. This is the fig of simulation circuit. Look at a toroid, some of toroid. This is a result of experiment in a laboratorium. Next, from analysis in above, we can take the conclusion. The magnetic field energy along the power line can be utilized as alternative electrical energy using toroid. From the analysis through a linear approach that in power line will large current up to 100 of amperes can be obtained power up to several kilowatts at 220 volts. The greater the electrical current that flow in the power line, the greater the magnetic field energy around the power line. Second, the more toroid is installed along the power line, the more net electrical energy will be obtained. And three, utilizing magnetic field energy in power line will reduce the public's image of the danger of the electromagnetic field radiation near the power transmission line. It is a simulation circuit in laboratorium. We used several toroid to lighten a lamp and several lamp incandescent lamp and electronic lamp with the ampermeter and voltmeter and clamp meter. And finally, That's all this paper that I can present. And finally, I say, sincerely, author Jacob Liklikwatil, Safrudin, Givi Devira Ramdhani, Ninik Sri Lestari, Herawati S. Rahmat Hidayat, Sekolah Tinggi Teknologi Mandala, Bandung, Universitas Kristen Maranatha, Bandung, Indonesia. Assalamualaikum warahmatullahi wabarakatuh. Peace to all of you. Thank you very much. Sudah selesai.